Hello, linear algebra student. This video is for chapter 4.4, part 2. Continue with bases. So in this video, we will have one more example on changing between the standard base and the new base B using the formula, and also we'll talk about how we can use whatever we know about changing bases to look at changing bases in other vector space such as polynomial. So the last example show that this base is -1, 2, 0, 3, -5, 2, 4, -7, 3 is a basis for R3, and then use the change of coordinate matrix to find the write the change of coordinate matrix PB. So B is pretty easy. So actually to show that it's a basis, we will use whatever that we learned in 4.3. How do we do that? We would because we have 3, we would form the matrix, have them all line up. Oh, -1, 2, 0, 3, -5, 2, 4, -7, 3. We have to check whether these columns are independent as well as span out 3. If both are okay, then it is a basis, right? So because of IMT, it is a 3 by 3 matrix, so we can use IMT. If I can reduce row echelon it into an identity matrix, then it will satisfy both conditions for linear independence as well as of spanning. So we would just need to enter it into the matrix formula, matrix calculator. -1, 2, 0, 3, 5, 2, 4, 7, 3. So matrix B here for -7, 3. And I do a RREF of, where is RREF? Maybe I'll just do this one. Delete this and then do RREF of B. So it is a identity matrix. 1, 0, 0, 0, 1, 0, 0, 0, 1. So by IMT, the vectors, the column vectors are independent, which is the requirement for a basis. And also that is what E or something, forgot. I forgot one of the condition number, and also it would span out 3, right? So hence, it is a basis for out 3. B is a basis for R3 because that's actually the 2 requirement, 1 and 2. Part B, find the change of coordinate matrix PB from B to the standard matrix. So PB is actually just the base, just all these vectors, column vector line up in a matrix. Because when we know the coordinate based on this, that's how we find A, where X is equal to PB times XB. This is the coordinate of X relative to B. So this is our formula that you need to remember. So now they say that, oh, I know something, a vector that has a -4, 8, -7 based on B. What is the vector in standard form? So we just use this, right? So it's a multiplication. So we just do 1, 2, 0. -1, 2, 0. 3, -3, 2. 4, -7, 3 times -4, x 7. So that means -4 times of the first one plus 8 times of the second one plus -7 times of the third one. You can do it by hand, or you can actually do like use the matrix calculator to do. Do I have it? I have it enter -1, 2, 0, 3, 3. Is it 3, 3? 3, 5. Oh, 3, -5. -5. 3, 5, 2, 4, negative 7, 3, multiply. So it would be just B multiply C, right? So I'll put it here. I'll do B. Oh, where is B multiply C? Oh, here. I just put it here. B multiply C. Right, so it becomes 0, 1, negative 5. 0, 1, negative 5. So the real matrix, the real vector x is actually 0, 1, negative 5, but in relative to the base b here is negative 4, 8, negative 7. Okay, so that is just a multiplication. Now, if I know x, I want to find use inverse matrix to find the coordinate xb relative to the base b. So we know this formula, x equal to pb times xb. And if I know this and I want xb, so xb would be what? PB inverse. Oh, PB inverse. Erase this. Should be PB, not BB. P of B inverse times x would equal to xb, right? So I have this enter, and I need to enter x, which is 8, negative 9, 6. Do I have 8, negative 9, 6? Maybe I'll use this. 8, negative 9, 6. A faster way actually is to solve by augmented matrix, right? 8, negative 5, 6. Oh, negative. Oh, 8, negative 9, 6. And I want to do B inverse times C, right? Because I would need to do B inverse. So it's 5, 15, negative 8. So this is the new coordinate according to this B. Another method would be second method, which is my preferred method, is actually just to do the RREF of the 1, negative 2, 0, 3, negative 5, 2, 4, negative 7, 3, and then solving for 8, negative 9, 6. So do I have it? I don't have. Oh, here I have negative 1, 2, 0, 3, negative 5, 2, 4, negative 7, 3, 8, 9, 6. So you can check if I do the REF of D, it will be 5, 15, negative 8. So it's the same, right? So it become 1, 0, 0, 5, 0, 1, 0, 15, 0, 0, 1, negative 8. So it's the same. So in your classwork, if I didn't say that you use inverse matrix, you can use you can use the RREF also. So that is all the work that all the example that I want to do basically is for this formula. A vector in a standard form is equal to the change of base matrix times x of b, where the change of base matrix is all those spaces in vertical column. So that's very good. So we are going into the second part of 4.4, which is using what we have learned about the new basis to understand a vector space using what we learned for Rn, change of base in Rn, to understand how we can use change of base in a vector space, not involving vectors in Rn, but actually generally any vector space. So in particular, we use a polynomial as an example, but it could be generalized to anything you want. So for example, so that means if B is a basis for vector space, we use blue to represent it, such as a polynomial or anything, then the coordinate mapping of x to xb can be understood as a one-to-one linear transformation from V onto Rn. That means I have a base here, and I how do I name this x in this space? It's the same as I name xb when everything is transformed in Rn. So for example, under the new basis, a vector in U is C1 times B1 up to Cn times Bn, and another vector is V equal to D1 B1, like that. So the coordinate mapping means instead of writing it this way, I can write U as a vector mapping, coordinate mapping of C1 to Cn, and V as corresponding to a vector in Rn as D1 to Dn. Okay, so now by vector addition, U plus V would be adding the scalar multiplication, or the scalar multiplication. Then the mapping of this kind of mapping is a linear transformation. That means whenever you have U, you can map it like this. Is a linear transformation, because T of U plus V would this would be just this one would become C1 plus D1, C2 plus D2, right? All those. And it's the same as C1, C2, Cn at D1, D2, Dn, right? So this is the first requirement for linear transformation. And then if R is a scalar, obviously R times U is the same as R times T of U, because the transformation is to change this writing of the combination of the bases into a vector column. So this vector column is a linear transformation, and also because it's so important, it has a name called isomorphism. That means anything that is in a vector space written in terms of the basis can be written as a Rn vector, and it's an isomorphism, is a linear transformation. So that means vector space V, any real vector space V, because R is a real number, is indistinguishable from Rn. You can treat it as an Rn vector. So for example, in polynomial, we have a standard basis of 1 t squared tn. We proved it in the last section. Now this can be mapped as a standard basis of e1, e2 to en plus 1 of Rn plus 1. And this linear transformation of isomorphism would say if I have a polynomial 4 negative 2t plus t squared, it would correspond to a coordinate mapping of 4, the first one, negative 2, and 1. When we write the polynomial, we usually write in descending order. So like that. So they are actually the same thing, or indistinguishable. Whatever operation you did on them is the same as you did in Rn. So all operation in P2 in the polynomial vector space corresponds to operation in R3. Okay, so if it is up to degree 2, it would correspond to R3 because you have a t to the 0. So there's one more coordinate than Pn. Example 1. Use the coordinate vector to determine that these are linear dependent. So this is a set of polynomial, but I can write them as they are the same as a set of vectors of what? 0, 1, negative 1, 0, 2, 7, negative 3, because I would just use the coordinate, right? So this is 1, and this is a negative 1. This coordinate is 2, and this coordinate is 7. You can see that I just use the coefficient. This is a negative 3. This coefficient is 1, 3, and a negative 1. So the last one is 1, 3, negative 1. I want to check that it is linear dependent. How do I do? So we would do an augmented matrix of 0, 1, negative 1. See if we can solve the equation of ax equal to 0, right? Solve this. Oh, I don't think I have enough time, so I'll do this in the next video.